Now, a minute ago, I said the probability of a die landing on 1 is 1/6. The probability of a die landing on 6 is 1/6. So the probability that a die lands on a 1 or a 6 is what? 2/6. You added, and then, of course, you could reduce. What about this? If you're going to roll the die twice, what's the probability that you land on a 1 the first time and land on a 6 the second time? Anybody want to take a wild guess? 1 out of 36. Multiply those two probabilities. All right, so when you're looking for probability of A or B, you add. When you look for probability of A and B, you multiply. The basic multiplication rule is used for finding the probability of A and B, and that means that A occurs in the first trial and B occurs in the second trial. The kicker is the second paragraph. If the outcome of event A somehow affects the probability of B, then you have to take that into account and adjust the probability accordingly. I'll tell you how in just a minute. But in my example of rolling a die, does landing on a 1, your first roll, in any way affect whether or not you're going to land on a 6 the second roll? No, they're completely independent of each other. Well, that's actually the next definition. Two events are called independent if the occurrence of one does not affect the probability of the occurrence of the other, and they're not independent if if one happening does affect the probability of the other happening. Now, I'm getting just a couple of slides ahead of myself when I tell you this, but think about sampling without replacement. If you had 10 marbles in a bag, 4 of them were blue, then the probability that you reach in and randomly grab a blue one is 4 out of 10, right? On your second, if you don't put that blue one back in, what's the probability of the next one being blue? Not 4 out of 10 anymore, but what? 3 out of 9. So if those two events are not dependent, and you would have to take that into, I said the wrong thing, not independent. They're not independent. They are dependent. You have to take that into account when you're calculating the probability. Dependent is the probability of one does affect the probability of the other, but that doesn't mean one is causing the other. The fact that you pull the blue marble out first is not going to cause you in any way to pull a blue marble out second, or not pull out a blue marble second. Classify as independent or dependent. Now, when we were looking at classify as joint or disjoint, we were saying on one trial, can both of these things happen? If not, then they were disjoint, and if so, then they were not disjoint. Here we're talking about 2 trials. Can these two, the one happening affect the probability of the other happening? If you go out to the driveway in the morning, turn the key, and your radio doesn't come on, what's your first thought? My first thought would be, oh no, especially if I know I had the radio on when I turned the key off. I'm thinking, oh no, my battery's dead. And I bet my lights aren't going to work either. As a matter of fact, I bet the whole car's not going to crank. These share a common power source. So this radio not coming on affects what I expect to happen with the headlights. Now, it's possible that the radio's just broken, but it does change the probability or your expectations about whether or not the headlights work because they share a common power source. So is that independent or dependent? Dependent. Now, that doesn't mean that your radio not coming on is going to cause your headlights not to come on. Just one happening makes you think, oh no, about the other. Number two, if you find out that your cell phone doesn't work, then you go, oh no, my car's probably not going to start. Not unless you believe in Murphy's Law. Murphy's Law is just everything that can possibly go wrong will. But aside from that, no, whether or not your cell phone works doesn't cause you to think anything about your car. So are those two events dependent or independent? Independent. Randomly selecting a consumer who owns a computer and randomly selecting a consumer who uses the internet. If you're doing a phone survey and you call somebody and say, hey, do you have a computer? And they say no. Does that affect the probability of whether or not they use the internet? Yeah, if you don't have a computer, yeah, you can go to the library, but it's also, it's less possible that you use the internet if you don't have a computer at home. So these two events are what? Dependent. Sampling without replacement leads to dependent events. For example, if you have 100 marbles in the bag, 40 red and 60 blue, the first marble you pull out has a 60% chance of being blue. Or you would say the probability of pulling out a blue marble is 0.6 if you wrote it as a decimal. If it is blue and I don't put it back in the bag and reach back in the bag and pull out a second marble, well, now there are only 59 blue marbles left out of 99 blue marbles total. So the probability that the next one is blue is just a little bit smaller. Every time I take a blue marble out of the bag, it reduces the probability that the next marble is going to be blue because there are less blue marbles. I'm taking them out of the bag and not putting them back. Each blue marble you pull out lowers the probability of the next marble being blue. That's what I mean when I say take into consideration if what happens on the first trial is somehow affecting what happens on the second trial. But then there's the 5% Cumberland, or 5% guideline for cumbersome calculations. I just need to slow down. This is something that you might not do in engineering or physics or chemistry, but you can do in statistics. If something is going to be very difficult to compute, like typing in the fractions 60 over 100 times 59 over 99 times 58 over 98 times 57 over 97, if I was going to draw out 10 marbles and I had to multiply those 10 fractions, would you agree that would be cumbersome? Yeah, I would call that cumbersome. As long as your sample is less than 5% of the population, as long as you're taking a small sample from a big population, then you can play like the events are independent and it's really not going to affect your calculation much. So you could play like you're putting the blue marble back and the probabilities just staying the same. You can only use that play like, that pretend that they are independent if your sample size is less than 5% of your population. For example, if there are 150 chocolate chip cookies and 100 Oreo cookies in a jar, and you randomly pull out 8 cookies from the jar, what's the probability that you get all Oreos? Well, what's the probability that the first cookie is an Oreo? Oreo. No. 100 out of 250. 100 out of 250 would be the probability that the first Oreo, the first cookie I draw out is an Oreo. And if I don't put that one back, the next draw, there are only 99 Oreos out of 249 cookies. And the next draw, there are only 98 Oreos out of 248 cookies. Multiplying these 8 fractions would be cumbersome, especially if I didn't have a calculator. It'd be horrendous. Yes. And I corrected it. Yes, I corrected it. Make sure make sure this is what your paper said. If you printed it this semester, it's correct. Last semester, I had a mistake there. So let's see if we can use the 5% guideline. Let's see if we can play like the events are independent. Well, I can only do that if my sample size is less than 5% of the population. What's my sample size here? I'm drawing out 8 cookies out of how many? Out of 250? How would I find out what percent that is? 8 out of 250. Just divide. 8 divided by 250. I thought I had it. 0.032. No, 8 divided by 250. That's 0.032. What is that as a percent? I just say change 0.032 to a percent. It's 3.2. That's less than 5%, isn't it? It's as long as it's less than 5%, I can play like those events are independent. And instead of multiplying these 8 fractions, I'm going to say, let's play like I'm putting the Oreo back every time. The probability is going to stay 100 out of 250 every time. Well, this wouldn't be any easier to punch on the calculator than this is, because you're still multiplying 8 fractions, except for you have a exponent button. That exponent button makes it much easier to punch this than to punch that. All right, so let me make sure you know how you're going to enter that. Well, actually, I typed it. On the calculator, you have to have that 2/5. I could have put in the 100 over 250, but since I could reduce it in my head, I did. Wouldn't affect the answer. I reduced that to 2/5. You have to have the 2/5 in parentheses, and then look for that caret button, that up arrow on your calculator. I call that your to the button. It's your exponent button. So 2/5 to the 8th. Somebody tell me what you get for that, and give me 3 decimal places. Okay, I have an excellent question. If a question in the homework is, what's the probability of blah, 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 could the answer possibly be 6 point something? No, and why not? No, that's not it. It's not between 0 and 1. If the question is, what's the probability, the answer has to be between 0 and 1. So did you punch that wrong, or is there something at the end of that answer that you're not noticing? Ooh, that's when you have to look. Hey, first you have to recognize that can't be right, and then look at the calculator again and go, ooh, there's that E. And that E means this number's in scientific notation. It's e to the negative what? -4, which means do what? 4 places to the left. And then if you round that to 3 decimal places, what's that answer? Would it round to 0.007? Let me punch it real quickly. I want to look at this because some folks don't have their calculators with them and they're frowning at me. 2/5 in parentheses is 2 divided by 5 to the 8th power is 6.5536 e -4. Move that decimal place to the left 4 places and then round to 3 places. And this 5 would cause that 6 to round up to 7.007. All right, that's what you should have for the probability that all 8 cookies you draw out are Oreos. Now, does that number disappoint you if your favorite cookie in the whole world is an Oreo? What's the probability that you're going to get 8 Oreos out of that jar? very, very low, 0.007. You're probably going to have to eat a few chocolate chips before you get 8 Oreos. Not that that's entirely a bad thing.